7, it's on chemical reactions and balancing chemical equations. And then being able to describe chemical reactions. All right, so here is an example of a classic chemical reaction that occurred that you may have done like when you were in high school or middle school. When you take baking soda, you add acetic acid or vinegar, and you get a volcano. So it fizzes and bubbles. You get carbon dioxide forming. There's a chemical reaction that has occurred. You had a solid and a liquid, and they came together, and now you have a gas. So this is specifically a gas evolution reaction. Here's another example of a chemical reaction. This is a combustion reaction. So octane, which is a component in gasoline, octane because it has 8 carbons, combines with oxygen in the atmosphere. It runs through your engine. We combust it. It produces heat, which we use to run our engine. And then it also, out of your tailpipe, you get carbon dioxide and water. This is a type of combustion reactions are a subcategory of what's known as an oxidation reduction reaction. And we'll talk about that a little later. Laundry detergent helps to create a precipitate to clean out gunk from your clothes. Okay, so evidence of a chemical reaction. If we could see what was happening on an atomic level, we would for sure know that a chemical reaction has occurred because we could actually see that the atoms are combining to form new compounds. We're getting new molecules, original molecules are decomposing, or atoms are swapping places. If you're undergoing a chemical reaction, you're going to get some sort of new material, whether you break a compound up into its simpler form or you combine things together into a compound form. But our eyes can't see this, so we have to look for secondary evidence that indicates that a chemical reaction has occurred. We've talked about some of these things, but a color change, not always, but a lot of times if you see a color change, that can indicate that a chemical reaction has occurred. The formation of a precipitate or the formation of a solid. So if I had a previously clear solution and I mixed it with another clear solution, then all of a sudden I get a solid clumping up at the bottom. That's a good indicator that a chemical change has occurred. Also the formation of a gas. And this, I don't mean this like we're heating up water, but I mean, we have 2 things at room temperature and we put them together like an Alka-Seltzer in water, and we start to get a gas forming. It's a good indicator that a chemical change has occurred. Anytime you produce light, is a good indicator. So here we have a glow stick. You take that glow stick and you snap it or you break it to allow the 2 chemicals to mix, chemical reaction. And then the emission or absorption of heat. So if we get a change in temperature, that lets us know. So over here on the left, we have a precipitate. This is some sort of iron oxide. And then we've got a clear liquid. When they mix together, we're getting this clumping or this solid forming. And then on the right, we've got that Alka-Seltzer forming a gas, both evidence of chemical reaction. This is not evidence of a chemical reaction. Yes, we are getting bubbles. Yes, it is turning into a gas, but it's turning into a gas because we are applying heat or we are applying energy to it to phase change it. And again, this is a phase change. So what is in the liquid form and what is in the gaseous form, it's the same thing. It's still H2O molecules. It's not like these H2O molecules have now morphed into something different. They've just changed phases. So we don't classify this as a chemical reaction. So at the end of the day, only some sort of chemical analysis that shows us what we started with and what we ended with would tell us that a chemical reaction has actually occurred. Okay, so how do we represent that something has undergone a chemical reaction? We do this with a chemical equation. So if like the symbols for the elements, those are the letters, and then we put those together to make compounds, and the compounds are the words, then a chemical equation is going to be a sentence. So we're going to start to combine chemicals together in an equation. So you will always have your reactants on the left side. So reactants, and you read this like you would read a book, left to right. So reactants on the left, an arrow will separate your reactants from the products, which are going to be on the right. How many reactants will you have? You have to have a minimum of 1. You could have a lot. You could have 2, 3, 5, 20. Products, same thing. You have to have at least 1 in order for it to indicate that a chemical change has occurred. But you can have more than that. A lot of times the state is specified after each reactant in parentheses. So like if I was to say, let's say one of my reactants was CO2, I'd go CO2, and then I'd put a little G after it in parentheses to let the reader know that it's a gas. I get lazy sometimes putting phases in, just know that. So here are the different symbols: G for gas, L for liquid, S for solid. And then we have this other one that you might not be familiar with, which is AQ. That means that the material is being presented to the reaction in an aqueous form, or it's dissolved in water. So I'm going to write sodium chloride, NaCl. And if I put a little S next to it, that means that I'm presenting it to the reaction as a solid, like table salt. If I write it like this, NaCl, and I put a little AQ next to it, it's not going to be introduced to the reaction as that solid salt form. It's actually going to be introduced as a solution, or in its like liquid form. So know that this means that it's just dissolved in water. Why does water solution get its own little phase? Because so many reactions on Earth happen in aqueous solutions because we have a plethora of water. Okay, so here is a chemical equation. This is the combustion of methane. So a reaction occurring in natural gas flame is methane, and it's methane, and it says it's reacting with, so that's sort of acting as a plus or an addition, oxygen. Okay, so we've got our methane, and it's reacting with oxygen. Anytime you see the word to form or to produce or create, that's your arrow. Okay, so to form, and then we have carbon dioxide and water. These are the 2 products. If we were to add the phases, in this case, they're all gases. I don't expect you to know like the phases on things. I don't expect you to have every compound's phase memorized at room temperature, so don't get caught up too much on that. But if we were to add it, it's methane is a gas. It's combining with gaseous oxygen to produce CO2 and water vapor out of your, well, this isn't in your car, but if this had been octane, it would be out of your tailpipe. So this equation is correct in that it's the right reactants and the right products, but it's not balanced. Do you guys remember the law of conservation of mass? It says in a chemical reaction, you cannot create or destroy matter. So you can't just make atoms up out of thin air and they can't just disappear into thin air. What you start with in a chemical reaction has to equal what you end with in a chemical reaction. This is not true for nuclear chemistry, and nuclear chemistry matter can actually change purely into energy. But for the sake of this, we need to make sure that the atoms we're starting with are equal to the atoms that we're ending with. So if we look at that equation where we had methane plus oxygen produces CO2 and H2O, if I just look at the oxygens, I have 2 oxygens in my diatomic here. On the ending side, I have 3 oxygens. I've got 2 on the CO2 and 1 happening in the water. Well, where did that other oxygen come from? You can't just like create oxygen out of nowhere. You had to have had that from your initial reactants. Just like you can't make 10 cakes with 1 cup of flour. You've got to have enough flour to do it. So there is a missing oxygen here. The same thing is true for hydrogen. Okay, except it's the other way around. Here, I had 4 hydrogens to start with, and I only end up with 2 hydrogens at the end. That doesn't work. Can't just have 2 hydrogens disappear. We need to take into account those hydrogens. So what we have to do is something called balance our equation. Now, when we're balancing a chemical equation, you can only add a coefficient. A coefficient is going to be a multiplier or a number that sits in the front of your formula. Okay, so it's something that goes in the front, and it's got to be a whole number. So like, you know, hey, I'm going to have 2 of these diatomics instead of just 1, something like that. You do not change subscripts when you are balancing chemical equations. So I'm going to show you just right now, if I've got 4 hydrogens here and 2 hydrogens here, I cannot do this, okay? I can't cross that off and make it a 4. What is H4O? It's definitely not water, so you're no longer honoring what the material is. So don't change subscripts, only add coefficients. So when balancing this, well, if instead of having 1 methane, 1 diatomic oxygen to produce 1 CO2 and 1 water, I'm actually going to take 1 methane. I'm going to combine it with 2 diatomic oxygens to produce 1 CO2 and 2 water molecules. If we go through this, we'll see that now it's balanced. I have carbons, hydrogens, and oxygens. How many carbons do I start with? 1. How many carbons do I end with? 1. How many hydrogens do I start with? 1, 2, 3, 4. How many hydrogens do I end with in this case scenario with the 2? I have 1, 2, 3, and 4. So we're balanced there. And then the oxygens, 1, 2, 3, 4. And 1, 2, 3, and 4. So by adding a multiplier here and here, I now have equal numbers of atoms on both sides. Again, I didn't change any of the coefficients, or I didn't change any of the subscripts. I just added a coefficient. When you're looking at the coefficient, it applies to everything within the formula. Okay, so that 2 needs to get multiplied by the hydrogen. So 2 times 2 would give you 4. It also needs to get multiplied by the oxygen. Okay, so they took inventory and everything equals it out. A balanced chemical equation represents a chemical reaction. In this image, we have methane. So methane, 1 methane molecule will combine with 2 oxygen diatomics to produce the 1 CO2 and the 2 waters. Now, how do we write, or rather, how do we balance an equation? The first thing you need to do is write a skeletal equation by writing the correct chemical formulas. This is all your nomenclature stuff, step 1. We're going to kind of skip over this for right now. We'll come back to it. So let's just assume we have a skeletal formula. And when I say a skeletal formula, I mean something like this, where you have your compounds in the correct place, but you don't have equal number of atoms. Okay, so if a couple rules, if you have an element that occurs in only 1 compound on both sides of the equation, balance it first. If there is more than 1 such element, usually balance metals before nonmetals. So do you all see here how oxygen is in 1 thing on this side, but then oxygen is in 2 things on this side? We would want to leave oxygen to the end. We want to balance everything else and hope it works out and then go to the oxygen if we need to. But because it splits up like this, it can just get kind of messy. So we would want to balance the carbons and the hydrogens first. If there happened to be a metal, you'd balance the metal first. If an element occurs as a free element on either side of the chemical equation, balance it last. So oxygen here. Another reason we would leave oxygen to the end is because it's by itself. So when I put a coefficient here, it won't affect any of the other materials. So I just want to leave that at the end, kind of as like the icing on the cake. I balance my carbons, I balance my hydrogens, and then hopefully I can just slap a coefficient on there and balance my oxygen and be done. If the balanced equation contains a coefficient or a fraction, so like if let's say you had 1.5, change these into whole numbers by multiplying it by an appropriate factor. So if you had one of your coefficients was 1.5, you'd want to multiply everything by 2 to get rid of that. Check to make certain the equation is balanced by summing the total number of atoms in each side. I'm going to show you guys how you can kind of do that as you go along, so you don't have to check at the end. And then remember, change only coefficients. Coefficients, don't ever change subscripts. So let's say we have, let's say we have aluminum, and it's going to combine with oxygen to produce aluminum oxide, which is Al2O3. All right, so the first thing I like to do is take inventory of everything I have. So I have an aluminum and I have an oxygen. Don't write sulfur down, don't write carbon down because you don't have those. Then I put a number on each side of these symbols to tell me how many of them I have. So here I have aluminum, I only have one of them. On this side, I have two aluminums, so I'm going to put a 2. Okay. Here I have oxygen, I have 2 on my reactant side, and I have 3 on my product side. So now I want to balance this, but again, I can only put things in front to balance the equation. So I could start with aluminum. I've got 2 here. I could put a 2 here, and that will change this to 2. Oxygen's kind of funky, right? So I've got 3 here, and I've got 2 here. So I could put 3 over 2, because 2 times 2, or rather 3 over 2 times 2 would give me 3. So now I have 3 there. Now we don't like halves. So what I want to do is multiply everything by 2. Multiply this by 2. That's going to apply to this coefficient, and this coefficient. So this becomes a 4. This becomes a 3. And this becomes a 2. Now let's add it up. Aluminum, we're going to have 4 aluminums. We're going to have 6 oxygens. Over here, the 2 goes times the 2. That gives me 4 aluminums. The 2 goes times the 3. That gives me 6 oxygens, and I'm done. Let's do another one. Let's do the synthesis of sodium chloride. So I have Na plus Cl2 produces NaCl. Okay, so we take inventory of what we have. I've got sodium, Na. I've got chlorine, Cl. In the equation currently, 1 sodium to start, 1 sodium to end. 2 chlorines to start, 1 chlorine to end. The sodiums are already balanced, so I leave them alone. The chlorine is not balanced. I have 2 on this side. I only have 1 on this side. So I'm going to put a coefficient of 2 here. That changes the chlorine to 2. It also changes the sodium to 2. That's okay if something is balanced and then it becomes unbalanced. We can rebalance it. If I put a 2 here, that then changes this to 2. And look, now our atoms are equal. Note that there's no coefficient written in front of the Cl2, but it's an inferred one. Okay, so there's an inferred 1 right there. I wouldn't have written it if I didn't have 1. Let's do another one together, and then I'm going to have you do a couple on your own. Sorry, I can't think of these like right out of my head. Let's what I'm gonna do. Okay, we could do CH4 plus Cl2 produces CCl4 and HCl. So if I want to balance this, I take inventory of everything I have. I've got carbons, I've got hydrogens, and I've got chlorines. 1 carbon to start with, 1 carbon to end with. 4 hydrogens to start with, only 1 hydrogen to end with. 2 chlorines to start with, and 5 chlorines to end with. Carbon's already balanced, so we can leave that one alone. Chlorine splits up. Do you see how chlorine is in one thing here, but here it's split between 2 things? I'm going to leave chlorine to the end. So let's balance our hydrogen. There's 4 on this side. So I want to have 4 hydrogens on this side. So if I put a 4 in front of here, that will change my hydrogen to 4. It also changes my chlorine though. There's 4 chlorines here, and now there are 4 chlorines here for a total of 8 chlorines. Thank goodness, because this isn't a multiplier of 2. So what can I stick in front of this thing to get 8? If there is Cl2, well, I put a 4 there, and that now changes this to 8. So we're ping-ponging back and forth to get the same numbers. Again, the system says, oh, check and make sure that you've got the correct number of atoms on both sides. You kind of are already doing that as you move through it. So I'm going to have you guys do a couple of these on your own, and then we'll come together and work through them. All right, so let's have you all do 1, 2, 3, 4, and 5. We'll stop at 6 because there's a polyatomic and I want to show you that. So yeah, do the first 5. Take inventory of what you got and then only mess around with coefficients to get what you need equal on both sides. Yeah, we'll do the first 5. I'll give you all okay. So this first one here, I'm going to just try and squeeze my notes on this page. We've got nitrogen and we've got hydrogen. I start with 2 nitrogens and 2 hydrogens. I end with 1 nitrogen and 3 hydrogens, not balanced. So we want to get it balanced. You know, I'm not going to start with the hydrogens. There's a 3 here and a 2 here. So I'm just going to do the nitrogen first. 2 balances this to 2 and then gets the hydrogen to be 6, which is a multiplier of 2. I always like multipliers of 2 when I have a diatomic because I have to have a multiplier of 2 on this side. I put a 3 here. That changes this to 6 and we're balanced. Yes? No? What is in front of the nitrogen? Know that there's an inferred 1 there. Next one here. I have calcium, chlorine, and oxygen. I start with potassium. I start with 1 potassium. I end with 1 potassium. I start with 1 chlorine. I end with 1 chlorine. I start with 3 oxygens and I end with 2 oxygens. So this is another example where I've got a diatomic, so it's a multiplier of 2. There is nothing that I can put in front of this to, there's nothing I can put in front of this that's going to give me a 3, right? I mean, I guess I could put a 1.5, but I'm going to put a 2 here to get this into a value of 6. So that's going to change potassium to 2, chlorine to 2, but then it changes my oxygen to 6, which I like because I can make this 6 over here by putting a 3 here. That changes this to 6. And then a simple fix for my calcium, I don't know why I want to keep calling it calcium, potassium and chlorine is to throw a 2 there. 2 and 2. This here, we've got sodium, Na, we've got chlorine, Cl, and we've got fluorine. I start with 1 sodium, 1 chlorine, and 2 fluorines. I end with 1 sodium, 1 fluorine, and 2 chlorines. I like when I see like 2s on both sides. Usually means it's going to be kind of a quick fix. So I'm going to leave sodium alone for right now. I'm going to balance chlorine. Well, I start, I end with 2 chlorines. So I need to start with 2 chlorines. I'm going to put a 2 in front of that. That changes my sodium to 2. That's okay. Changes my chlorine to 2. Then I can balance the metal here. So I'm going to put a 2 in front of the sodium over here, which changes my sodium to 2. And then it also changes my fluorine to 2. And now everything is balanced. I've got the synthesis of water here. Hydrogen, oxygen. I start with 2 hydrogens and 2 oxygens. I end with 2 hydrogens and 1 oxygen. Hydrogen's already balanced, so let's balance the oxygen. Well, if I throw a 2 in front of here, that changes my oxygen to 2. It does unbalance the hydrogen, makes this 4. That's okay. Quick, easy fix. Let's just throw a 2 in front of that hydrogen. And now we are balanced. This last one here, we've got lead, Pb, we've got oxygen, we've got hydrogen, and I've got chlorine. Okay, I start with 1 lead. I start with 2 oxygens. And then this is important. You start with 3 hydrogens. So that 2 applies to both things in the parentheses. There's 2 hydrogens here, and don't forget about this. This is the 3rd hydrogen. Okay, so 3 hydrogens. And I start with 1 chlorine. You want to make sure you're taking inventory correctly in the beginning. If you're having a really hard time balancing, you may have added things up incorrectly. All right, I end with 1 lead. I end with 1 oxygen. I end with 2 hydrogens, and I end with 2 chlorines. So currently lead is balanced. Oxygen, I'm going to balance oxygen next. I'm going to stay away from hydrogen right now because do you see how hydrogen, it's on one side, it's in 1 compound on the product side, but it's in 2 compounds on the reactant side. And that's kind of messy. And so we just hope we can fix the other stuff and then it'll be okay. So I'm going to put a 2 here. That's going to change my oxygen to 2. Oxygen is now balanced. It's going to change my hydrogen to 4. Let's leave hydrogen and go to chlorine. I have 2 chlorines on the end, so I need to have 2 chlorines to start with. So let's put a 2 in front of there. That changes my hydrogen to now 4, right? 2 from here and 2 from here. And then it also changes my chlorine to 2. And now we're balanced. Everything's good. We end there. Again, inferred ones in these places. So if you have a polyatomic ion and it doesn't change, it stays intact, you can take inventory of the polyatomic ion as a whole. So do you see how sulfate here, SO4, it stays sulfate, SO4, we just happen to multiply it by 3. That's different than what's happening here. Here we have OH, and then now on the product side, there is no OH anymore. So you cannot use this technique in that case. But if your polyatomic ion stays intact, take inventory of the polyatomic ion as a whole. Don't break it up. So when I take inventory for number 6, I'm going to go, hey, I have aluminum, I have bromine, I have potassium, and then I have SO4. To start with, I have 1 aluminum. To end with, I have 2 aluminums. To start with, I have 3 bromines. To end with, I have 1 bromine. To start with, I have 2 potassiums. To end with, I have 1 potassium. And to start with, I have 1 sulfate ion. Now, if you want to break it up into sulfurs and oxygens, you can, but if it stays a whole polyatomic ion, I would just treat it as a unit. So I start with 1 sulfate. How many sulfates do I end with? I end with 3 sulfates, right? The 3 applies to the whole packet. So I'm going to put a 3 there. So let's start balancing. Usually you start with metals before non-metals. So I'm going to do the aluminum. Okay, on this side, I have 2 aluminums. This side I only have 1, so I'm going to throw a 2 in front of here. That changes my aluminum to 2, which is now balanced. It changes my bromine to 6. So we could go ahead and balance bromine if you want. Bromine, on this side, there's only 1 and I need 6 of them. So I'm going to throw a 6 in front of it. That changes bromine to 6. It also changes my potassium to 6 because that coefficient applies to everything within the compound. Okay, well, we can balance the potassium now. If there's 6 potassiums on this side, I need to have 6 potassiums on this side. An easy 3 in front would get me to the 6 potassiums. And then look at that. It also gives me 3 of the sulfates. So now we're balanced. So I like to clump my polyatomic ions together. If that doesn't work for you and you want to take inventory of all your sulfurs and oxygens, just make sure you're multiplying everything out. So this is not 1 sulfur and 4 oxygens. It's actually 3 sulfur and 12 oxygens. I'm going to give you one. I'm going to give you something with a polyatomic ion, 2 polyatomic ions actually, and I'm going to have you balance it. My whiteboard. So let's say we have calcium nitrate, CaNO3 plus lithium phosphate, Li3PO4. And this thing produces lithium nitrate, LiNO3, and calcium phosphate, Ca3PO4. 2. There are 2 polyatomic ions in here, nitrate and phosphate. I want you to go ahead and balance this. I'll give you a minute or 2. Taking inventory of this, I kind of think of there as being 4 things: calcium, nitrate, lithium, and phosphate, which is PO4. So that I don't have to count up all these oxygens. There's a lot of oxygens. I don't want to have to manually count those all out. And I don't have to because they stay clumped together in their polyatomic packets. So let's take inventory. There's 1 calcium to start with. There's 3 calciums to end with. There are 2 nitrates to start with, right? The packet is in parentheses and we've got a 2 on the outside. Over here, I only have 1 nitrate to end with. There are 3 lithiums to start with. There's 1 lithium to end with. There's 1 phosphate to start with. And then there are 2 phosphates to end with. I like this, how there's 2s and 3s on both sides. I know that I'm going to get a common factor. It'll get me to 6 for some things. We can start with calcium. So there's 3 calciums on the end. So I need to have 3 calciums to begin with. I'm going to put a 3 in front. That's going to change this to 3. It's going to also multiply my nitrates by 3, which is going to give me a total of 6. Okay, so now I have 6 nitrates. I can go ahead and balance my nitrates. If I put a 6 over here, that's going to change my nitrate to 6. It also changes my lithium to 6, which is totally fine. If I want to get to 6 on this side, I need to put a factor of 2 in the front. That changes this to 6. It also changes my phosphate to 2. So we balance that second thing and we're all balanced. Any questions on balancing with a polyatomic ion? You can only do that if the polyatomic ion stays as a whole. If the polyatomic ion breaks up or there's like other stuff kind of messing with it, like you have oxygens in the polyatomic ion, then oxygens outside the polyatomic ion shifts, don't do this. But if it's pretty clear cut like this, there's my nitrate, there's my nitrate, there's my phosphate, there's my phosphate, just treat it as a unit. So let's talk about that first step. Where I said you need to write a skeletal formula. So you're not always given a skeletal formula. So here, write a skeletal equation by writing the correct chemical formulas for each of the reactants and products. Let's pull up the sheet here. Sometimes things are given to you as a word problem. So we've got this mess here. Something like sodium combines with chlorine to produce sodium chloride. You should be able to write a balanced equation for that. How I attack these is I underline everything that I know is like a compound or a thing that I'm going to have to write out. So I have sodium. It combines with chlorine. Combines is usually your plus symbol. To produce. So anytime there's a to produce or to form or decompose, that's my arrow. Okay. And then in the end, I'm going to get sodium chloride. So now I need to write a skeletal formula. The first thing is just to write the correct chemical formulas. Don't worry about balancing, just write things the way they're supposed to be written. So sodium has a symbol of Na. Ask yourself, is sodium a diatomic molecule? You always, anytime something is by itself, ask yourself if it's a diatomic. That's the hydrogen, nitrogen, have no fear of ice cold beer, hydrogen, nitrogen over down to iodine. Sodium is not a diatomic molecule, so it's just going to exist by itself. If we want to put a phase in, you can say it's solid. I'm not super strict on that. It combines with chlorine. Okay, so chlorine is Cl. Now, is chlorine a diatomic molecule when it's by itself? Yes, it is. That means that chlorine will never be, when it's alone, it's never going to look like this. It's always going to look like this, Cl with a 2. Does that make a difference? Oh yeah, it makes a difference when you're balancing your equation. If you forget the 2, you're going to think your equation's already balanced when it's not. To form, to produce sodium chloride. So I need to charge neutralize sodium chloride. Sodium is Na with a plus charge. Chlorine is Cl with a minus charge. Flip flop, it's a 1-to-1. So I'll get NaCl. So that's the first step, is just going from the things to an actual skeletal equation. Now I can balance it. I've got 2 chlorines here, so I need 2 chlorines here. That now makes me have 2 sodium, so I'll put a 2 there and we're balanced. Let's look at number 6. Aluminum reacts with oxygen to produce aluminum oxide. So aluminum reacts with oxygen to produce aluminum oxide. The first thing I want you to do, I want you to take a minute and just write each of these things out in a skeletal formula. Then we'll balance afterwards. I'll give you just a minute to write out the correct things. Okay, so first step is to write things in the correct places. So aluminum reacts with oxygen. Aluminum is Al. All right, I'll give it a phase. It's a solid. Reacts with oxygen. Okay, so that's going to combine with oxygen. Is oxygen just an O? No, it's O2. Oxygen is never going to be presented in elemental form as just O. It's O2. So know your diatomics. This is a gas. It's going to come together to produce aluminum oxide. What I see a lot happen, don't write this down, but what I see a lot happen is people go, oh, aluminum oxide, ALO, and I'm done. Nope. You've got to charge balance. So a metal and a non-metal, Al with a 3+ charge, O with a 2- charge, flip-flop. I'm going to get Al2O3. You guys remember that stuff from the nomenclature chapter? Yeah, it's not going away. Sorry. So we balance. Now, if you don't have the 2s correctly, if you don't have these correct, you're going to have a hard time balancing it correctly. But now, go ahead and balance this. If you didn't get these correct, have them written correctly now, and then go ahead and balance the equation. Okay, so as far as balancing goes, we only have 2 things. We have aluminum and oxygen. I start with 1 aluminum, I end with 2 aluminums. I start with 2 oxygen, I end with 3 oxygens. I can already see this 2 and 3 discrepancy here. So I know I'm gonna have to put a 2 here to get this to a multiplier of 2, which would be 6. That changes this to 4. I can put a 4 here, and then I can put a 3 here, and we are balanced. I want you all to do this one, number 3. Sounds scarier than it is, okay? Solid iron 3 oxide and carbon monoxide gas produce iron metal and carbon dioxide. I want you to write the correct, zoom out a little bit. I want you to write the correct skeletal formula for that, and then I want you to balance it. And here, I'll even help you guys. I'll underline the materials. You should have 4 materials. Figure out which side goes on the reactant, which side goes on the product, and then balance. I'll give you all 2-3 minutes for that. All right, so I forgot this one's kind of a pain in the butt to balance a little bit. If you have trouble balancing it, it can be a little bit tougher. Okay, so we have iron 3 oxide. Iron 3 oxide. It's combining with carbon monoxide, CO, to produce iron and CO2. I've got to figure out what my iron 3 oxide is. So iron 3 means that we have Fe with a 3+ charge. Oxygen will always be a 2-, flip-flop. We get Fe2O3. That should be this first guy here. So Fe2O3. So I've got, just make sure that, okay. So I've got iron, I've got oxygen, and I've got carbon. I start with 2 irons, I end with 1 iron. I start with 4 oxygens, 3 from here, 1 from there. And with 2 oxygens, I start with 1 carbon, I end with 1 carbon. So when balancing, I can balance the iron first. I've got 2 here, so I'm going to put a 2 there and balance that out. Oxygen, I have 4 here. and I only have 2 here. So if I put a 2 here, that's going to change this to 4. It's also going to change my carbon to 2. Okay, so I could put a 2 here. That's going to change my oxygen now to 4 or 3, 4, 5, and my carbon to 2. Well, this is always going to be a multiplier of 2. So what is the next number that I could put in front of here to get to an even number? If instead of 2, I put a 3, that would change my carbon to 3. That would change this to 6. I like that because then instead of a 2 here, I can put a 3 here. That changes this to 6 and it changes this to 3. That one kind of had to be like massaged a little bit. All right. Sometimes they're a little bit tougher. Usually you guys probably on your exams won't get anything that's tricky like that for balancing. So questions on balancing chemical equations. On the whole idea of it, your mastering chemistry should give you some practice with it. And the lab should give you some practice with balancing as well. Right, let's move on to some of the different types of chemical equations, like classifying them by what they're doing. One question here. Why does it seem like oxygen is always a problem element in these? Cynthia, oxygen just tends to split up or exist in multiple compounds, and that's why it usually tends to be a problem. And we sort of just leave it to the end. But oxygen can like break off pretty easily and combine with other things. Okay, so aqueous solutions and this concept of solubility. So when a solution is quote unquote aqueous, AQ, it means that the compound is soluble in water. What does soluble mean? Soluble means that a particular liquid or a particular material, can be a liquid, could be a solid, dissolves in a liquid. A compound is insoluble if it doesn't dissolve in the specific liquid. An aqueous solution, again, is a homogeneous mixture with water. Usually when ionic compounds dissolve in water, they will what's called dissociate or break up into their component ions. So if I have something like sodium chloride, NaCl, and I have NaCl aqueous, so I'm telling the reader, hey, this isn't like table salt sitting on your countertop, but this is table salt that's been dissolved in water. What that means is that I'm going to have Na pluses and Cl minuses floating around in the solution. They break up into not just sodium and chlorine, but the sodium ion and the chlorine ion. So we have a bunch of ions floating around in solution. Sodium chloride completely dissociates. That means that every sodium and every chlorine breaks apart. This makes this solution known as a strong electrolyte solution. So have you guys heard of electrolyte water? And we spend extra money for it. And all electrolyte water is water with some sort of dissolved salt in it, right? Our bodies need these electrolytes. They need these salts in our bloodstream. You can make your own quote unquote Gatorade by taking some water and putting some dissolved salt in it and adding some lime juice and a little sugar if you want. Why do we call them strong electrolyte solutions? Well, if I was to take a light bulb and connect it to a battery, and then, but I didn't have a complete circuit. Instead, I took these 2 cathodes and I stuck them in a container of water. If it's pure water, the light bulb won't run because there's nothing for this current to transfer over. There's no bridge or connection. If I have a strong electrolyte solution, these electrolyte or charged particles can actually carry the current of the electricity through. So, sorry, if I have a battery, I can complete the circuit with electrolyte water and the light bulb will light up nice and bright. You cannot electrocute yourself with a hairdryer in a tub of pure water, but you can do it in a tub of salt water. Okay, you would need the dissolved ions to transmit the electricity. Let's say we have something that contains a polyatomic ion like silver nitrate, AgNO3. This thing is going to break apart into silver, Ag+, the silver ion, and the nitrate ion, NO3-. Okay. The polyatomic ion itself isn't going to break apart into nitrogen and oxygen. That bond between nitrogens and the oxygens is a covalent bond. They're sharing those electrons. It's way too strong for water to pull that thing apart. So we will always keep our polyatomic ion as a packet. So let's say I had calcium carbonate, CaCO3, and say this thing was aqueous. It would break apart into calcium with a 2+ charge and carbonate, CO3, with a 2- charge. Let me say aqueous. Yes. All right, we keep the polyatomic packet together. What happens when we get something like this, AgCl? Silver chloride. Silver chloride is not soluble in water. It would be written something like this. It'd say AgClS within the liquid water. It means that it's staying a solid. So I drop this thing into solution and the silver and the chlorine are so attracted to each other that the pull of the water can't break them apart. So it wouldn't dissolve. So we would just have a big hunk here. So there would be no ions floating around in solution. So if I stuck my cathode in with my light bulb, I'm not going to be able to transmit the electricity through. There's no ions in it. So how do you know that silver chloride doesn't dissolve in water, but you know that silver nitrate does? Well, there's a bunch of rules. I don't expect you to have these solubility rules memorized. You just need to be able to reference them. They're usually in an appendix in the back of the book or in this specific chapter. Here are some of the solubility rules. So most of these materials are soluble. Like, for instance, the lithium, sodium, and potassium from column 1, ammonium, nitrate, and acetate. These things, it doesn't really matter what they're combined with. They're always going to be soluble. Now, chlorine, bromine, and iodine are mostly soluble, but they have a couple exceptions. So if your chlorine happens to be mixed or combined with silver, mercury, or lead, it all of a sudden clumps or becomes insoluble, or it forms a precipitate. So that's what's happened in that previous slide. Here is silver came together with chlorine. That is a magic combination that creates something insoluble. Sulfate, for the most part, is a soluble material unless it happens to be combined with these things. Again, these are, a set of tables, rules. I would not expect you to fill your brain with all this information, but you do need to be able to reference it. There's another chart here. These things are mostly insoluble. So OH, or hydroxide, usually is insoluble unless it's combined with lithium, potassium, and sodium or ammonium. Then if it's in that case, then it tends to be soluble. If the compound contains sulfur, again, it's usually insoluble unless it's paired up with things from column 1 and column 2. And then the last one, carbonate and phosphate, tend to be insoluble unless they're combined with one of these. So you just need to be able to reference the charts. Here's some other ways of expressing the same thing. So we can have reactions where we can actually see a precipitate forming. And a precipitate reaction occurs when two aqueous things come together and a solid forms, or precipitate forms upon mixing them. So let's look at this equation here. We have potassium iodine, which is aqueous, comes together with lead 2 nitrate, which is also aqueous, and bam, right here. Do you see how all of a sudden one of the products is a solid? That means that this lead and this iodine, when they get together in that aqueous solution, they attract to each other so much that they will precipitate out, or this will form a solid. So what's happening here is I have a clear liquid, and then when they mix together, the iodine from the top thing and the potassium from the bottom thing in the flask start to come together to form this solid. Pretty easy to identify that it's a precipitate reaction because something aqueous combines with something aqueous and we get something solid. The other thing here happens to be aqueous, and that doesn't necessarily indicate that there's a precipitate, but the lead iodide does. So looking at this thing, when I have potassium iodine and I mix it with sodium chloride, I don't get any reaction. Why? Well, I need to figure out what my potential products would be. So you can think of this like a dating scenario. We have couple A and couple B, A and B. And they decide to go to a party together and they've had too much to drink and they break up, okay? Are the couples going to get back together? Not really, because they're aqueous. They already broke up. So potassium and iodine don't want to get back together, and sodium and chlorine don't want to get back together. So they're going to swap partners pretty much. Potassium is going to take a look at chlorine and say, hey, why don't we see what happens? Okay, so KCl. And then sodium is going to get with iodine, say, hey, do we want to come together? So these are your potential products. Well, I'll tell you right now, both of these things are aqueous. So there's no magic happening here. Okay. Neither of those want to be with each other either. So everything just stays broken apart. So they all went to the party and they all left alone. That's why there is no reaction here. Now, when you're getting your potential products, and you can see this happened on the last slide as well. So we have, couple A and couple B, and potassium, or the metal from the first set, mixed with the non-metal from the second to produce potassium nitrate. You have to balance charges. So this is a +1 and this is a -1. That's why it's a 1-to-1 ratio. They weren't really into each other because the solubility charts told us that they were aqueous. But lead decided to get together with the iodine. It produced this, and if we look at the solubility charts, that makes a solid. So they're sort of like a swinger situation, okay? They swap partners, but they're conservative in their swingerhood. So it will always be metal with non-metal. It will never be metal with metal, okay? Or non-metal with non-metal. Why? Metals and metals both have positive charges, so they're not going to work. Non-metals and non-metals have negative charges, so they're not going to work. So they're always going to switch partners, but keep that positive negative charge thing happening. So let's decide. So this is kind of a more expanded version of what happened. So here's couple A, and they've already started drinking, right? We put them in the water and they've already broken up. Couple B's already broken up as well. Then they decide to go to a party together, and they're all in the room together. Potassium has already, potassium came with iodine. So potassium doesn't want anything to do with iodine, but it's going to try and get together with nitrate, and they don't really work. It's when lead and iodine meet. That's when that bond is so strong that we end up getting a precipitate. So I want you to tell me what the potential products are for this precipitate reaction here. Sodium carbonate, which is aqueous, is going to come together with copper 2 chloride. Write out the two potential products, make sure they're charge balanced. they're charge neutral. So you have the correct number of metal to non-metal. I'm gonna give you 2 minutes for that. It even gives you the arrows to show you what needs to combine together. Okay, so the two potential products that we need to look up on our solubility charts, sodium combined with chlorine. I find that it helps some students to write, if they write the charges above each of the things they're combining in the beginning. So sodium has a +1 charge, carbonate has a 2- charge. Copper here has a 2+ charge because chlorine has a 1- charge and there's 2 of them, right? So that's where the 2+. So I want to flip-flop charges. Sodium is a +1, chlorine is a -1. So I'm going to write NaCl. Don't worry about like balancing just yet, just write your potential products. The next one is copper, which has a 2+ charge, with carbonate, which has a 2- charge. So my other potential product is CuCO3. From here, we want to look up on the solubility charts whether it's aqueous or not. Well, I'll tell you right now, NaCl is definitely aqueous. Okay, that's AQ. CuCO3 is, in fact, a precipitate. It's a solid. I wouldn't expect you to have that memorized, right? But you need to be able to reference it. So the last step is to balance it. Do you guys see how there's 2 sodiums here and 2 chlorines here, but only 1 sodium and 1 chlorine here? I'm going to put a 2 in front of there to balance it out. So flip-flop partners, see what your potential products are, look them up on a solubility chart, and then balance if need be. So these were our potential products, and we found that that was in fact a solid. If both of your products are aqueous, you would just write no reaction, okay? So if all potential options are all aqueous, it means nobody's getting together. That's like this situation right here. Potassium iodide and sodium chloride, when I flip-flop partners, nobody likes each other enough, so they just all stay in aqueous, so there's no reaction. This equation right here is called a molecular equation. I'm going to write this on my whiteboard. Na2CO3 aqueous plus Pb. I forgot what it was already. Cu. Okay. Okay, so this is a molecular equation. Molecular equation. What that means is that everything's written in its molecular form, or you have even the things that are aqueous, like we know that they're broken apart into their ions, but we're clumping them together. There's another way we can write this equation, and it's called, you write molecular equation up here, molecular equation. The next way we can write this is something called the complete ionic equation. Sometimes I call this the complete pain in the butt equation because it is a total pain in my butt to write these out, but we do need to know how to do them. So in a complete ionic equation, what you're going to do is take anything that's aqueous, that would be this, this, and this, and you're going to break it apart into its ions. Okay, break it apart, break it apart. So follow me here with this one. I've got Na2CO3. I want to break that into the ions. So sodium's ion is Na with a plus charge. How many sodiums do I have? In this case, I have 2 of them. All right, so I'm going to take that 2, I'm going to put it in front. I have to write a little AQ. Okay. Then I've got this thing, which is carbonate. All right, I'm going to add carbonate, which is CO3. Don't forget to put the charge. This is the complete ionic. Ionic meaning you're adding its charge, right? Or its ions. This thing is also aqueous. I'm going to break the next thing up. Copper, Cu, and in this case, it has a 2+ charge. This thing's aqueous. Chlorine, Cl with a minus charge. This thing is aqueous. Put the 2 in front. Now I know when chlorine is by itself in elemental form, it comes as a diatomic, but I'm not talking about it in its elemental form. I'm talking about it in its ionic or charged form. So we don't put the 2 there. We move the 2 in front. All right, so this got broken apart. This got broken apart. Put an arrow. We got to break this thing apart now. Okay, sodium and chlorine. So I've got sodium, which is Na plus aqueous. How many of them do I have? There's a 2 in the front, so let's put a 2 there. Plus the chlorine, Cl with a minus charge, aqueous. I have to put a 2 in front of that one as well because the 2 gets distributed out to both things. Finally, thank goodness, this is a solid. I just get to write that the way it is. CuCO3, solid. You see how this is a total pain in the butt to write out? So many aqueuses, so many, so many little AQs. You got to know how to do it though. So there's one final type of equation because the complete ionic equation breaks everything up, but then we have these things called spectator ions. Do you see how the sodium here and the sodium on the product side are the same? Like they're not actually doing anything. They're just sort of delivering the important stuff. Same thing with chlorine. Chlorine is, these are all known as spectator ions. Spectator ions. They themselves are not included in the quote unquote chemical reaction. They're just delivering the other stuff. So my final type of equation is known as a net ionic equation. The word net meaning like, let's say you went from AB Tech to the Biltmore estate, but instead of going in a straight line, you drove all the way around Asheville like 6 times, and then you went to the Biltmore estate. Your drive would be really long, but your net change would not, right? You only went maybe half a mile. Same thing here. We're just looking at what's doing the main work. So we take our spectator ions and we just cancel them out. So let's cut out sodium and let's cut out chlorine. What you have left is the important stuff for your net ionic equation. I'm going to write the metal first. Cu2+, aqueous. So when copper with a 2+ charge comes together with carbonate with a 2- charge, that's where the magic happens, right? It's aqueous and it's aqueous. Bam, they come together and they're going to form CuCO3, solid. Instead of delivering the carbonate with sodium, I could have delivered it with potassium. Instead of delivering the copper with chlorine, I could have delivered it with fluorine. Those, again, are just acting as spectator ions. So 3 types of equations. You got to be able to do those. I will have you do an example in just a second. Let's look at what they have on the slides here. They give a couple examples as well. All right, they've got silver nitrate combines with sodium chloride to produce silver chloride and sodium nitrate. So molecular equation is when we have our neutral formulas. Complete ionic equation, anything that's aqueous. So this thing, and this thing, we're going to break up into all the aqueous. And then we keep this as a solid. We keep that intact. To get the net ionic equation, we want to find our spectator ions. So in this case, the spectator ions were the sodium and the nitrate. Here it's by itself, here it's by itself, by itself, by itself. This coming together with this is what makes the magic precipitate. That is the important thing. So our net ionic equation just includes really the important stuff. And we can see here, silver gets together with chlorine to produce silver chloride. I'm going to give you one of these to do. I'm going to give you the molecular. I want you to write the complete ionic equation and the net ionic equation. Yeah, okay, so Cu SO4 aqueous plus 2NaOH aqueous comes together and produces Na2SO4 aqueous and CuOH2 solid. Bam. This is a precipitate reaction. Aqueous, aqueous, solid. Okay, here we've got our molecular. I want you to do the complete ionic and the net ionic. And I'll give you guys 5 minutes for it. So if you need to take a break or a bathroom break or whatever, you can do that as well. The lecture should move pretty quick after we get through this concept. So we should be out of here by 8:10. Okay, so let's break these things up. And actually, even before we break it up, let's just write a charge above everything. So if I kind of cut this thing in half, sulfate has a 2- charge. Copper has a 2+ charge. They need to balance each other out. Hydroxide has a -1 charge. Sodium has a 1+ charge. So breaking this up, I've got copper, Cu. It should have a 2+ charge, and you write a little AQ. There's only one of them. Sulfate, SO4, with a 2- charge, and this is aqueous. Remember, your polyatomic ions stay together. We're going to add this to sodium, which is Na with a + charge. There are 2 of them because there's a 2 sitting in the front, and this is aqueous. Plus the OH-, and there's also 2 of those, and that thing is aqueous. All right, we're going to equal that out. So whatever's on this side needs to equal whatever's on that side. So sodium, I've got 2 sodiums, Na plus aqueous. Sulfate, SO4 with a 2- charge, and it's also aqueous. There's only one of those though. plus my solid. I don't have to break my solid up. So I just write it as CuOH2 solid. That's the complete ionic equation. Now, to get to the net ionic equation, I need to remove any spectators. So sodium is acting as a spectator. Sulfate is also acting as a spectator. They aren't involved in the actual chemical reaction. So copper, Cu with a 2+ charge, it's aqueous, comes together with 2 hydroxides, OH minus aqueous, and we produce precipitate, CuOH2 solid. Any questions on precipitate reactions or complete ionic or net ionic equations? All right, so we're going to move on to the next type of equation that we have, which is an acid-base neutralization reaction. Okay, in an acid-base neutralization reaction, you have some sort of acid. How do you know that this is an acid? There's an H sitting in the front of it, okay? When the H is in the front, acid. Combines with a base. How do you know this is a base? For right now, your definition of a base means you're going to have an OH on the back end of it. There are other things that can be bases, and there are things that contain OH that don't have bases, but really you guys should be okay. If you see something with an H in the front and an OH in the back end, that's an acid combining with a base. Now, these are always the 2 products that you're going to write. You're going to have a water. So you'll write water with a liquid, and then you have a salt. The salt is going to be all the remaining stuff. So do you see how here's the hydrogen and here's the OH? Those 2 things together are what make the water. The stuff that's left over, the metal here and the non-metal here, are what make the salt. And when I say salt, what I mean loosely is a metal and a non-metal, right? Or something ionic. Sometimes we refer to ionic things as salts. So if we had a different set of things here, let's say instead of hydrochloric acid, we had hydrobromic acid, HBr. And I combined that with potassium hydroxide, KOH. And I said, hey, tell me what the products are going to be. You need to be able to write the products out. One of them better be water, H2O. The other one is going to be the salt with the remaining stuff. So in this case, it's a potassium and a bromine. So plus KBr, and this thing is aqueous. The potassium and the bromine, again, are just acting as a delivery system for what's really doing the chemical reaction, which is this thing and this thing coming together to form water or neutralizing. An acid-base neutralization reaction takes something with a high pH and combines it with something with something with a low pH and combines it with something with a high pH to get a neutral pH. Or like if your stomach is feeling really acidic, what do you take? You usually take like a Tums, or you can drink some milk, something that's kind of basic to neutralize the stomach acid to make it less acidic. If I was to take these things and break them apart into a complete ionic equation, and then create a net ionic equation, for all acids and bases, this is going to be your net ionic equation. What's really important is that you have H+, which is the acid thing, coming together with OH-, which is the base thing, to create H2O, which is your neutral liquid. Some acid-base neutralization reactions will produce what's known as a gas evolution reaction. Oh, FYI, here's some acids. What do you see with all these things? H in the front, H in the front, H in the front, okay? That's your indicator that it's an acid. Here are some bases, OH on the back end. Really OH with things from column 1 and column 2. So sometimes when you mix acids and bases together, you can get what's known as a gas evolution reaction. And this is where you have an acid, it combines with some sort of base. You produce water, a salt, and you produce a gas. I am not expecting you to predict the products of a gas evolution reaction. Okay. I do expect you to be able to predict the products of like something like this. I could give you this, and you'd be able to tell me those are the two products. Why? Because if it's acid base, you're going to get water and a salt. This is a little bit above your guys' pay grade. So for gas evolution reactions, all I really want you to know is that you have something that's aqueous and then bam, a gas pops out. It's just an identifier. Just be able to identify that that would be a gas evolution. But I don't expect you to write products or anything like that. So the next type of reaction is a redox reaction or an oxidation reduction reaction. Redox reactions are responsible for like when you oxidize metal or you rust iron, when you bleach your hair, the charge that you get in a battery, all our combustion reactions, anytime we're combining a hydrocarbon with oxygen. These are all examples of redox reactions. And a redox reaction is really just a reaction where an electron is getting transferred from one thing to another. I don't expect you to identify redox reactions. I don't expect you to tell me what's being oxidized and what's being reduced. I just want you to understand it on a concept level. So there's two mnemonics that can be helpful. I tend to just stick with oil rig. Oil rigs tells me that oxidation is loss. Specifically, oxidation is loss of electrons. Okay, reduction is gain of electrons. What I'm writing right now is not what I would expect you to be able to do. I'm just using it as a way to explain this concept, okay? So let's say I have sodium, and it's combining with chlorine to produce sodium. Let's make that a 2. Sodium chloride. Okay, I'm going to put a 2 here, a 2 here, so it's balanced. So when sodium is like this as a solid, it has a neutral charge. Okay, I didn't write a charge in the upper right-hand corner, so this has a 0 charge. Chlorine, when it's in its diatomic form or its molecular form, also has a charge of 0. What happens when they come together? There's an exchange of electrons, right? So in this, sodium has a charge of +1, chlorine has a charge of -1. So how did sodium go from a 0 charge over to a +1 charge? It had to lose 1 electron. In order for it to, or there's 2 of them, so each one lost 1 electron. So if it lost an electron, oxidation is loss. Sodium here is being oxidized. Okay, so Na is our oxidized. Oxidized. Chlorine had a 0 charge, and now it became a -1 charge. In order to do that, it had to gain an electron. Reduction is gaining. So this thing was being reduced. Again, I'm not going to like write an equation and say, hey, what's being oxidized and what's being reduced, but I'm just using this to help explain what's happening here. One thing loses the electrons. That means it's being oxidized. One thing gains the electrons. That means it's being reduced. In an equation, you have both of those happening simultaneously. If one thing is losing an electron, another thing has to be gaining an electron. So oxidation and reduction must occur together in the same equation. You're not just going to have one thing being oxidized with nothing else there. Something else has to be like reducing it. That is all I'm going to do for oxidation reduction. It's pretty much just definition based. It's not going to be identifiers. Some examples of oxidation reduction reactions: anytime something reacts with elemental oxygen, a metal reacts with a non-metal. That was what we just looked at, sodium reacting with chlorine, or one substance transfers electrons to another. This thing here, combustion reactions, this is a type of redox reaction. This I do expect you to tell me what the products are on. But it's not that hard because it's the same throughout. It doesn't really matter what the hydrocarbon is. It's always going to combine in the same way. So let's write methane, which is CH4. I would have to give you methane because I know you don't know organic naming. Or let's do propane. Yeah, let's do propane. C3H8. Okay. Either one of these, they undergo combustion. This is what you're going to do. You're going to add oxygen. Okay, I'm going to add O2. That stays the same. My two products are always going to be CO2 and H2O. Plus, like heat. I mean, that's why we're combusting it. So we have heat as well. But that doesn't really play into balancing it. So same thing with this one, CO2 and H2O. Doesn't matter what the hydrocarbon is. This is the remaining portion of it. You take your hydrocarbon, you add it to oxygen, you get CO2 and H2O. Then you have to balance it, okay? So we have carbon, hydrogen, and oxygen. 1 carbon to start, 1 carbon to end, 4 hydrogens to start, 2 hydrogens to end, 2 oxygens to start, 3 oxygens to end. When you're balancing combustion reactions, this is the way to do it. First, balance your carbon, then balance your hydrogen, then balance your oxygen. It just seems to work out better that way. So I have 1 carbon on this side, I have 1 carbon on this side. 4 hydrogens on this side, I need 4 hydrogens on this side. So I'm going to put a 2 in front of my water. I change my hydrogen to 4. It changes my oxygen to 4 as well. There's 2 here, plus the 2 that are going on here for a total of 4. Thank goodness, because it's much easier to balance 4 over here. I just put a 2 there, and that makes it 4, and we're balanced. Let's balance this one. Again, carbon, hydrogen, oxygen. 3 carbons to start, 1 carbon to end, 8 hydrogens to start, 2 hydrogens to end, 2 oxygens to start, and 3 oxygens to end. Balance carbons, then hydrogens, then oxygens. 3 carbons here, so let's put a 3 here. That changes this to 3. It changes my oxygen to 6, plus the 1 over here for a total of 7. Oxygen is a mess. Let's leave it alone and do our hydrogens. I have 8 hydrogens here, so I need 8 hydrogens over here. If I put a 4 there, that will balance my hydrogen to 8, and then it makes my oxygen 10. I like 10 because this is a factor of 2, so I put a 5 here, and this becomes 10. Again, it doesn't matter what the hydrocarbon is, you're always going to combine it in this way. So let's say you have octane, C8H18. If I'm going to combust octane, I add it to oxygen, I will create CO2 and H2O, and then you just balance accordingly. Combustion makes sense? Don't stray from this, this, and this. Okay. Combine it with oxygen and give me these 2 products, and then balance. So that's the last type of equation or chemical reaction that you have. So it's precipitate reactions, acid-base reactions, gas evolution reactions, which really are just a type of acid-base, and I don't expect you to know a whole lot. Redox reactions, which again, I want you to know definition base, and then combustion reactions. I do want you to be able to write products and or balance it. There's another way that we can like layer a classification on top of these. So something can be an acid-base reaction and also be one of the following four things. Okay, so we have synthesis or combination, decomposition, single displacement, or double displacement. This is describing an equation based off of what the atoms are doing in their arrangement. We can go back to that sort of dating situation scenario. So synthesis or combination is where two people start dating. So we've got A and B, they meet up at a party and then they become AB. Okay. Decomposition is your breakup. So we have a compound AB and it breaks up into simpler components, A and B. And we have this one called a single displacement. This is like your home wrecker situation, okay? So you have a couple, B, C, and C decides that A looks better than B. So C and A get together and it boots B, right? In a single displacement, one thing is gonna be booted out. Again, make sure that the metal combines with the non-metal. And then the double displacement, that's the home wrecker situation, or no, that's the swinger situation, right? So we've got couple AB and couple CD, and they flip-flop partners. This is all the precipitate reactions you guys were looking at, the acid-base reactions, they're double displacements. So a synthesis reaction, really simple one, sodium and chlorine come together to produce sodium chloride. Two elements come together to produce a compound, synthesis. Decomposition, the breaking apart of water. So we can take water and run it through a battery. It's a pretty simple experiment. And we can actually break apart into hydrogens and oxygens. We had a compound. We now have the individual elements. We decomposed it. Here is a single displacement situation. So I have copper chloride dissolved in solution, and I have this zinc stick. The zinc is more appealing to the chlorine than the copper is. So what the zinc or what the chlorine is going to do is it's going to pull the zinc off of the stick, and it's actually going to deposit the chlorine back on the stick. So the chlorine and the zinc flip places. And then we've got double displacement. That's where we flip-flop partners. So synthesis, decomposition, single displacement, double displacement. Let's look back at that. Where were you? Those equations, these here. Okay, and let's just quickly go through and classify them by what their atoms are doing. So in this first one here, we've got nitrogen coming together with hydrogen to produce NH3. This would be a synthesis reaction, because two simpler things are coming together to form something more complicated. Here I've got KClO3, and it breaks up into KCl and O2. This is our decomposition. Number 3, look at what's going on in number 3. I've got a compound and a single element. This ends up, don't write home wrecker on your test, but this is the single displacement, right? So we get the F booting the chlorine. So now the Na and the F are together and the chlorine has been released. This here, H2 plus O2 produces H2O. We would say that this is another synthesis. Down here, we've got the hydrogens are coming together with the OH to produce H2O, and the lead and the Cl are coming together to form this. So this is a double displacement. They're flip-flopping. This one also is a double displacement, right? They're flip-flopping partners. Hopefully now you can start to look at these things and see what the atoms are doing. Hopefully you can start to see 7 and 8. What type of chemical reaction are both of those? Combustion reactions. Hydrocarbons coming together with oxygen, CO2, H2O. Okay. So that is the end of that chapter. Hopefully if you guys did some studying already, that cleared any questions up that you have. But if you have more questions, I am here. Otherwise, have a really awesome week/weekend. Your next test will be in about a week and a half. Okay, so we've got one more lecture that's going to combine all the stuff from chapter 6 and all this stuff into one big, lovely chapter called stoichiometry. So make sure you're here next Wednesday because it's an important lecture. Have a good weekend. All right, hear my dog. Stay around if you have questions. All right, bye. I was wondering if you have a video of this chapter lecture on YouTube. The one that we just did, like right now. Bye, Cynthia. I'll see you next time. I'm glad it makes sense. I will post this. So what we are currently saying right now will be recorded and put on YouTube by tomorrow. Awesome. And I did get your labs and they should be graded and updated in the system. So let me know if anything doesn't look good there.